Yes, when I was deciding what to present here today, I was thinking I wanted to present some of the work that's going on in my group, and I thought one of the things that connects a lot of the work in my group is the use of random effects. So just a quick definition: a random effect is an unknown latent variable assumed randomly distributed from a known distribution or known or assumed distribution, but where the parameters of that distribution are to be estimated from the data, often used to account for correlation in clustered data. And so I decided that for my role in this talk, I would try and play devil's advocate, something like the John Cleese role in the Monty Python film. And I would ask to the members of my group, what have random effects ever done for us? And I imagined that Marco Palmer from my group, who's in the audience somewhere, might shout out longitudinal data analysis. Okay, so going back to the beginning, if you like, this is a mixed effects model. So for repeated measurements of some biomarker, repeated measurements Yij, where I denotes the individual and J denotes the measurement occasion, and we can model that biomarker using a fixed effects term where the parameters beta are common to all individuals, and a random effects UI, which are assumed normally distributed around 0 with some covariance matrix sigma, and an error term epsilon, which is also normally distributed and assumed independent of the random effects. So what does this look like? Well, it might look like a random intercept slope model, for example, where the two individuals, this is data generated from a mixed effects model where the two individuals in the graph have different intercepts and different slopes, assumed normally distributed. So this model can be extended to a mixed effects location scale model. So the mean trajectory is exactly the same as we had before. We have a fixed effects term and a random effects term. But the epsilon I'm now interpreting as true variability around the mean trajectory. And I'm considering the case where that variability may be different for different individuals in the data set. Okay, so I've highlighted in red the parts of the model that are different from the usual mixed effects model. So the log of the standard deviation here is now specific to the individual I, and I'm assuming that is log normally distributed with some mean nu, which may depend on covariance. And this covariance matrix here, an unstructured covariance matrix, allows for correlations between the random effects and this random variability here. So what does this look like in practice? Well, going back to the same data, this is data generated from the same model, but now allowing the variation around the mean trajectories to differ, where the red individual has much more variable measurements than the blue individual. So why might you be interested in using this kind of model? Well, Marco's been looking at data from cystic fibrosis patients, cystic fibrosis being an inherited progressive condition affecting the lungs, the digestive system, and other organs in the body. And this paper by Morgan et al. In 2016 found that patients with greater variability in their lung function are at greater risk for subsequent decline, suggesting that quantifying FEV1, which is a measure of lung function, it's the forced expiratory volume in 1 second, quantifying the FEV variability may be beneficial in predicting future lung function decline. So Marco's using data from the UK Cystic Fibrosis Registry. This is a national database managed by the Cystic Fibrosis Trust. In total, over 12,000 patients, around 80% of the total of all the patients in the UK. They have annual clinic visits at which lung function is measured. And so this is the model that Marco fitted. I should say he used a Bayesian approach in STAN to fit this model. So in his location or mean submodel, so he has some baseline covariates xi, and he has a nonlinear dependence on the age at the visit, which is stratified by sex, and also nonlinear dependence on the year of birth. And the scale submodel for the variability, I should say there is a small mistake here actually. The sigma should have an I index on it as well as the epsilon. So the log of the sigma I is now equal to, again, the same baseline covariates and also nonlinear dependence on age and year of birth, and a random term here. And those random effects are assumed normally distributed as before. So the covariates, all the baseline covariates are listed here, and natural cubic splines were used to model those nonlinear dependencies. So these are the results from Marco's analysis. So we have the results for the mean trajectory on the top and the results for the variability on the bottom. So for the mean trajectory, we found that, so the blue trajectory is for males, the red for females. So males have consistently higher lung function than females, but lung function does decline rapidly with age. I should say this is only the model is only fitted to adults. So starting at age 18, lung function does decline very rapidly up to age 50. The year of birth dependence is quite interesting. There's this kind of cubic effect. And that's because there are two factors coming into play here. So there's a cohort effect whereby the younger patients have had access to better medicine throughout the whole of their lifetime. But there's also a survivor effect because this data, so our data set starts in the year 2000. And so the older people in this data set are the people who've survived up until the year 2000. So there's also a survivor effect. So the combination of those is kind of giving this cubic effect here. And then the graphs on the bottom show the dependence of the variability on these on the age and the year of birth. So again, males tend to have higher variability than females, and it declines with age, but then kind of evens out with possibly a slight upward increase in variability for older ages. And then the year of birth, again, has a nonlinear effect, kind of increasing and then decreasing. Okay, so moving on, I'm going to play devil's advocate again. I'm going to say, okay, apart from longitudinal data analysis, what have random effects ever done for us? And I imagine that Cedar Chen from my group might say joint modeling. So Cedar's particularly interested in multi-state modeling of multimorbidity. So this is the multi-state model that he's been working with. So each state in this model is defined by a combination of diseases. And this is focusing on diabetic patients. So we're interested in modeling the trajectory, the disease trajectory of diabetic patients, focusing particularly on transitions to cardiovascular disease in state 1. They may also transition to a mental health condition in state 2. And then from those two conditions, they can then acquire the other condition to end up in state 3 with diabetes, cardiovascular disease, and mental health. And we also have transitions to death from all those states. So the question Cedar was working on was to work out the association of all these transitions with blood pressure. And to do that, you can fit a joint longitudinal multi-state model. So the longitudinal model here is very similar to what we had before. It's a mixed effects model with some fixed and some random effects, which you can combine into this mu IT, which is the mean trajectory for individual I. Going back to a homoscedastic error term here. And then for the multi-state model, so this baseline hazard, I should say this is the hazard for individual I to transition from state K to state L in the model. And assuming a baseline, a proportional hazards model with a Weibull baseline here, and then proportionally dependent on the fixed effects. And then this association term, the alpha K L mu, characterizes the association with blood pressure. So there's an association there with the current value of blood pressure. And so these random effects are shared now between the between the transition hazards through this association term and also the longitudinal model. So the data CEDA's working with is data from the Clinical Practice Research Data Link, specifically their CPRD Aurum database. This consists of data from GP practices which use the EMIS software. And in total, there are over 70,000 people in this data set with incident diabetes. So this is the data set CEDA's working with. Now to fit this joint longitudinal multi-state model is computationally intractable to that size of data. Because in order to fit, I should say, CEDA's also using a Bayesian approach, which makes things easier for a joint model. But in order to fit this, you still have to do a numerical integration as a consequence of the shared random effects between the longitudinal and the multi-state model. So CEDA's been considering some alternative approaches. And the first approach he thought about was to use these, what we're calling blockwise competing risks. So instead of fitting the full joint multi-state model, he's fitting the model in blocks, where each block is defined by the state. So here we have block 0 for state 0, and the transitions coming out of that state. So it's a block 0 with the competing risks that are transitions from the state 0. So fitting that as a joint longitudinal competing risks model, and then also fitting in parallel block B1, which is defined by state 1 and the transitions coming from state 1. And then similarly for block B2, which is state 2 plus the transitions from state 2 to states 3 and 4. And then finally, block B3, which is just the transitions from state 3 to death. So by fitting all of these in parallel, we can make the problem a lot more tractable. He's also gone one step further and thought about, well, what happens if instead of fitting these blocks, you just fit all of these as single transitions. So fitting a separate joint longitudinal survival model for each of these transitions. And these are the results from CEDA's work. So these are applied to just a random subset of individuals, of 15,000 individuals. So this was the largest sample size that he could manage with the full joint model. So in order to compare the models, he restricted first to that smaller sample. So the thing to focus on is the graph in the left, which is the association parameters characterizing the association between blood pressure and the different transitions. And so we can see there are some differences here between the joint model, which the full joint model is in red, and the competing risks model is in green, and the single transition model in blue. Actually, one thing to say, one extra piece of detail, is that we've got two competing risks models, which are JMCRC and JMCRH. So in the model JMCRC, the longitudinal data that's used in fitting the model is restricted to the longitudinal data that was observed within the block. Whereas the model with the H at the end, that's H is standing for history, so for the later blocks, you can also use all past measurements to try and improve the fit of the longitudinal model. And the same for the single transition models here. So there is a slight difference here between the joint and the other models. One thing to say is that the joint model is not necessarily the gold standard here, because what the competing risks model does is it allows the longitudinal model to be adaptive, if you like, to transitions from one state to another, because a different longitudinal model is fitted to each block. The assumptions on the longitudinal model in the competing risks approach are actually less restrictive than the full joint model, which assumes that the longitudinal model fits to the longitudinal trajectory across the whole of the follow-up. And we also see some slight differences here between the models that use the full history and the models that use only the longitudinal data within the block. And that's possibly also indicating that there's some slight model misspecification when you assume that the longitudinal model fits to a longer period of time. For all the other model parameters, that the models are in pretty good agreement. I'm going to move on again. Okay, apart from longitudinal data analysis and joint modeling, what have random effects ever done for us? And I'm imagining that Danilo from my group might say dynamic prediction. So what do I mean by dynamic prediction? This is the situation where we want to predict the risk of an event over, say, an L-year time period. We want to use some measurement of an exposure to predict the event. But as time goes on, we want to update our risk predictions. We might have new measurements of the exposure. We know that the individual hasn't yet had the event at time t-pred. We want a new updated risk prediction. And again, as time moves on, more measurements, new information, updating the risk prediction at the new prediction time. So Danilo's been working on dynamic prediction in the context of multiple myeloma, which is a type of blood cancer that affects plasma cells. So in the interest of time, I'll just point out that one of the characteristics of multiple myeloma is a high level of M protein, which can be measured in the blood. So the aims behind Danilo's project are to dynamically predict the time to next treatment and survival using two longitudinal biomarkers, which are the M spike and the free light chains. And he's using flat iron data, which is a data set taken from multiple oncology clinics in the US. So Danilo's also been looking at a multi-state model. And he's looking at the states here are defined by the line of treatment that the patient is in. And the patient might move progressively. If the line of treatment 1 is becomes ineffective, they may move to line of treatment 2, so a new treatment, and then progressively to line of treatment 3, line of treatment 4. And then there are also transitions to death from all those states. So one of the characteristics of this longitudinal data is that it has this very non-linear effects, which you might see in the red here. So what happens is when the new treatment is started, the condition improves and the biomarkers kind of decline rapidly. But then there's a kind of a flatter period, but then they start to increase with time. And the increasing is a sign that the disease is now progressing again, and a new line of therapy needs to be started. So in order to reflect this data, Danilo's used a bioexponential longitudinal model. So in this longitudinal model, we have a baseline parameter B. D is a decay parameter, so this reflects that initial decline at early times. And then G is a growth parameter reflecting the increase in the biomarkers at later times as the disease is progressing. And so in the model Danilo's fitted, these are all treated as random effects. So there's an individual specific baseline, decline, and growth. And I should say here, so M here, the index M reflects the biomarker, so that's M spike or FLC, and L is the line of therapy that you're in. So we're fitting a different model, different longitudinal model to each line of therapy. And so that B, D, and G, these are all positive. So these are expressed as an exponential of a population parameter theta plus random effects B1, B2, and B3, which are assumed normally distributed. And so the survival model now, again, he's using a joint model, so those random effects are shared with the survival model. So the survival model is, again, a proportional hazards model with baseline H0 and a dependence on all the random effects, the B, the G, and the D from both longitudinal models. And Danilo's fitted a separate joint longitudinal and survival model for each line of therapy. I should say Danilo is also using a Bayesian approach, which he's programmed all of this in STAN. So I'm just waiting to see if this, okay, this slide should be longitudinally updating, but it seems to be. I will just have to describe what should be happening, I think, with this slide. These are the results. So the top two lines, if it was working, you would be seeing some longitudinal evolution of the M spike and the free light chains in the top two graphs, and the fit of the longitudinal model. So this is, I should say, this is dynamic prediction for a specific patient. And in the bottom graph, we have the cumulative incidence function for the two outcomes we're interested in, which are the time to death within the current line of therapy and the time to the next line of therapy. And as the longitudinal model evolves, you would see these predictions changing over time. And as you would see as the FLC and the M spike increase, you see an increase in the predicted time to next line of therapy, cumulative incidence function. So yeah, sorry that's not working today. Okay, we could go on. Okay, apart from longitudinal data analysis, joint modeling and dynamic prediction, what have random effects ever done for us? Well, people might shout out with other things, an informative observation, frailty modeling. And so just to conclude, random effects have proved a useful tool in the analysis of clustered data, including accounting for heteroscedasticity, as we saw in the mixed effects location scale model. For multi-outcome modeling, because they can account for correlation between multiple outcomes of different types using these shared random effect models, or even multiple outcomes of the same type, for example, a multivariate longitudinal model. And for in dynamic prediction, to allow dynamic updating of prediction models in response to new information learned about the individual in question. And the list goes on, and we are, I'm sure, yet to hear many, many more applications of these random effects tools. And I'll just leave you with thanks to all of our collaborators for the 3 projects that I talked about today. Thank you.
Any questions? Can I ask a difficult question? How do you assess the kind of fit of these models and whether they actually fit in the data well, or do well in terms of prediction?
Well, in terms of prediction, you can assess predictive accuracy using. So I didn't have time to present all of the work that's been done here today, but Danilo's been looking at assessing calibration using Breyer scores and calibration plots, and discrimination using the C-index. You can also look at the fits. So generally what's done is to look at the fit separately of the different outcomes using kind of standard residual techniques, for example.
Even in those separate blocks, when you split the models in each of those separate blocks?
Yeah, so when you fit the model in the separate blocks, you have a different longitudinal model that's fitted in each block, but you can still fit that. So CEDA was using leave one out cross-validation for some to decide between different models in that case.
Okay, so we have a question online from Abdul Majid. If you could please unmute yourself and say your question, please.
Oh, hello there, can you hear me? Hello?
Yes, we can hear you.
Okay, thank you very much. I do like the talk, so interesting. Just 2 questions. Is the first question the lung function? Have you tried a function in R called the lung function, the lung-Gamos function? Because I was with the team when they were working on modeling the lung data, and this is just a quote from a Japanese paper. They say the Gamos model approach is suitable for deriving the reference value for the lung function outcomes. And the second question, and this is I put here the paper of Gamos lung function in statistics in medicine, if you want to look at. And the second question, the ML model looks interesting. Have you adjusted for age and sex? Because this is different by male and female and different by age. Usually cuts from triggers in the males from age 70 above? Thank you very much.
Yeah, thank you for your questions. So Marco has been looking into, I think you said GAMLs, so Marco's been looking into BAMLs because he's using a Bayesian approach.
Oh, yes, yeah. We have BAMLs too, yeah, for the Bayesian approach, yes.
Yeah. So he's also used the Bayesian version for fitting those kinds of models. I think the difference is just in, well, Marco might explain better than me, but the difference I think is just the model is the same, just in the way the model is fitted essentially. But he is looking into the difference. So Marco's used a package called BRMS and STAN, and he is looking into the differences between the fit using BRMS and the fit using the BAMLs approach.
Okay, great. Is it published or going to be published, this result?
Not published yet, but hopefully
Okay.
go in the future.
Yeah, I'm keen to read it. Okay, thank you.
Okay, well, yeah, maybe send me an email and we can connect with you after.
Oh yeah, yes, this would be good because I'm always in contact with the GAMLs team.
Okay.
Thank you. And the second question is the MM I'd like to know more about it.
So was this still the cystic fibrosis model for lung function?
I'm just asking if you have you adjusted for age and sex in the model of the MM, the multiple myeloma model?
For the multiple myeloma.
Because it's very different in age and sex.
Yeah, I glossed over, but I had a list of. I'm pretty sure we have, but
Okay.
Barrett. I'm just trying to remember where I listed all the covariates.
Okay. So the plot which you're showing us here, this is the are this the IgGs or something, or they call them the plasma cells?
So sorry, Danilo's giving me a thumbs up. So yeah, we have adjusted for age and sex in the model.
Okay.
We have a question here.
Yeah, thanks. I like random effects models, and that was a nice overview of your work. I enjoyed that. When you're fitting these kind of more intricate random effects models, particularly like in the kind of joint modeling context, we and other people, I guess, have noticed a bit of brittleness to model misspecification and problems with feedback and things like that. I mean, so if you have some kind of random effects in some sort of longitudinal model and then put also those random effects in the outcome, then sometimes bad things can happen. I mean, due to this kind of brittleness to model misspecification. I don't know if you have some comments on how you think about dealing with those types of problems.
So, well, in all the models we fitted, we check things like convergence, the R-hat, and so on. I didn't have time to go into any of the details here.
I mean, yeah, this problem has nothing to do with MCMC mixing.
Yeah. I find that in terms of when we check for model misspecification, it seems to be fitting pretty well. I think sometimes if you run like a simulation study, you do find examples that don't converge. But we haven't had a problem in the fitting of the models, other than just that the kind of computational intractability on the whole. So CEDA ran some simulations for the multi-state model, and he found that the blockwise. So I think for the joint model in the simulation study, there were some instances where the model just didn't converge, compared to the competing risks, which is the kind of simpler model that does help with convergence issues and so on.
So we also have a hand raised online from Ayab Say. Could you please unmute and say your question?
Yeah, hi. Can you hear me?
Yeah, you can.
All right, thank you for a nice presentation and random effect, which is I'm using this random effect for living a life. So almost 30 years. I add some application. There are also application of random effect. In official statistics, they are calling borrowing strength, which they use for, they're getting, sample size. If they don't have enough sample size, they use a random effect, and then they can predict official statistic, ONS, using that method when we developed when I was at Southampton University. There is also other application, which is combining different data sets. You can use that random effect as well. So that's my 2 additional application random effect. Thanks for presentation.
Thank you for your comments. Maybe I should update my my what have random effects ever done for us statement. Yeah, so extra additional applications. Thank you.
If we have no further questions, we can probably move on. Thank you very much, Jessica.